Welcome back to Elementary Statistics. In this video, I want to introduce you to hypothesis testing using the z-test, which is perhaps the most straightforward test to use. It does have the drawback of being relatively limited in its value and its application, but that doesn't mean it's never applicable. Before we get to the z-test itself, I want to talk a little bit in general about hypothesis testing. We've been building up the entire course trying to get to this idea. The idea of hypothesis testing will be the driving force for the rest of the semester. We've seen that we can take a representative sample of a population, we can perform analysis on that sample, and with some confidence, with some probability, we can say that the results of our sample do a good job of representing the value of some variable in the entire population. The next thing we can do building up from this is use a statistical analysis to compare two different populations. The classic example here is a medical trial. Suppose that you have some sort of a new treatment for a disease. We have a known population, people who have had this disease and have been treated using the traditional means or whatever medication has already existed. That is one population. As a new population, we can take some patients and treat them with your new treatment method, your new medication, whatever it may be. And so we want to ask the question, does the new treatment method create a different measurement in whatever variables we can use to analyze how a patient is recovering compared to the old one? Of course, we can never say with complete confidence that this is going to happen. So just like with our discussion on confidence intervals, we're going to have some level of significance, some probability under which we can say that yes, these are two different results, or no, based on our probability, these seem to be the same result. All right, let me get my head out of the way and let's look at that a little bit more carefully. A statistical hypothesis is a conjecture about a population parameter. The conjecture may or may not be true, right? Any conjecture has a possibility of being true, a possibility of being false. Usually, in a statistical hypothesis, we're actually going to form two hypotheses. The null hypothesis is written as H subscript 0, read as H naught, N-A-U-G-H-T. But the null hypothesis is going to tell us that the population parameter is equal to some value. That is, there's no difference between the first population and the second population in this hypothesis, or in this situation. The alternative hypothesis, which many sources write as H subscript 1, sometimes you'll see it written as H subscript A. They're used interchangeably. But the alternative hypothesis tells us that there is a measurable difference between the results in these two populations. And there are two approaches you can take to a statistical hypothesis. There is a one-tailed test, and there is also a two-tailed test, or a two-tailed approach. And the two-tailed approach is going to be the one that we use most frequently. In the two-tailed approach, the null hypothesis tells us that the population mean mu is equal to some value k. Again, the value k here usually comes from another population, right? So mu is a population we are studying, an unknown population, and k is the mean or an equivalent value for a known population, a population that has been studied previously. And then the alternative hypothesis, H1, is simply that mu is not equal to k. Right? This is the form that we are going to use almost exclusively in this course. It's a little bit more strict, it's a little bit less general, and it gives us a little bit of interest in places to go. The one-tailed approaches show up in conditions where you are certain that the relationship goes in a certain direction, either that the population mean for your unknown population is bigger than the known value or is smaller than the known value. And by making an assumption in this direction, it gives us a little bit more flexibility. The test is a little bit less stringent, and there are places where that's valuable. But again, for our purposes this semester, I'm going to avoid the one-tailed tests. They'll show up every now and then, but by and large, we stick with the two-tailed approach just to be consistent and to have fewer different moving parts in the process of problem solving. Right. I've talked about this, but let's write it down. In most research situations, the language of a hypothesis test, the null hypothesis says that our new idea is no different from whatever is happening before. So if you're looking at a medical test, taking this new drug does not heal or has the patient recover at the same rate where patients recovered with the existing medications. The alternative hypothesis says that our new idea is measurably different from whatever exists. So again, in the medical case, that means that taking your medicine has a measurable effect on the rate of recovery. Now, this doesn't say it's a measurably faster effect or a measurably slower effect, just that it is doing something different. And most of the time in research, doing something different is our goal. So our goal is to come to the alternative hypothesis. If we can find a statistical reason to accept the alternative hypothesis and reject the null hypothesis, then we are happy. If it turns out that we will have to accept the null hypothesis, generally that means that the research has been inconclusive. There's another failure of statistics. If you reject the alternative hypothesis and accept the null hypothesis, that could mean that your new idea did not improve things any. It could mean that the data you collected is not sufficient to show an improvement. And that is something else I punt back to whichever discipline came up with the test in the first place. Knowing how to proceed when the alternative hypothesis is rejected, when the null hypothesis is accepted, is something that will vary from discipline to discipline. I'm going to try to give you some ideas on what measurements you can use to say Is this statistical test too weak? Can we make a stronger statistical test? Can we make a stronger statistical experiment to measure the values here in the first place? But that's for later. For now, let's look at the step-by-step process of performing a hypothesis test. I break down a hypothesis test in 7 steps, although the first couple are very quick, the last couple are a little bit lengthier. Before performing a hypothesis test, you have to have a question you wish to answer. I've said it a couple of times, but I'll repeat myself. Formulating your question is not in the purview of a statistics course. This is something that will come from whichever discipline you are studying where you are trying to do statistical analysis. I've used medical research as an example. You can perform a hypothesis test asking a question about educational research, about other scientific research, about economics. There are a number of places where you might want to perform a hypothesis test. Once you have your question, the next thing you want to do is determine how to approach that question. A hypothesis test is only really doable if you can collect numerical data to analyze. So you have to come up with a variable that should be measured. Very often this is going to be measure this value and find the mean of the sample, and we're going to try to predict something about the mean of the population for this variable. Sometimes we'll talk about things in proportion, sometimes we'll talk about standard deviation, and a couple of other ideas as well. But for the first couple of ideas, it's going to be the mean. Next, write your null hypothesis and your alternative hypothesis. These are generally very easy to write down. You have the variable that you are planning to measure and the population parameter, the mean or something else about that variable that you're planning to look at. The null hypothesis is going to be that that value is equal to some known value in another population. The alternative hypothesis is that they are not equal. Done. The next step is to choose an appropriate level of significance. This is the crucial step of the entire process. The level of significance is asking you, what probability are you okay with being wrong? The level of significance is the answer to the question, what is the probability that you made your conclusion by mistake? Or very specifically, what is the probability that the null hypothesis was true, but then you rejected it anyway? Which is not quite the same as the probability that the null hypothesis was false, but you accepted it anyway. Right. So very specifically, the level of significance is the probability that the null hypothesis is true, but you rejected it. We're generally going to use 0.05. And we'll represent the level of significance with the variable alpha. It's a Greek letter, kind of looks like a fish. 0.05 is the standard in medical research and in psychology research. There are other disciplines that use other values. 0.01 is fairly common. 0.10 is not uncommon, especially in biology research. In physical research, in physics, chemistry, we use much smaller values. High energy particle physics uses alpha equals 0.00001, which is not something that we can do by hand, so we're not even going to try. All right, but 0.05 is far and away the most common. And thinking about how probability works, if alpha is the probability that you have the null hypothesis being true, but you reject it anyway, well, 1 minus 0.05 is 0.95 or 95% confidence. If you use alpha equals 0.05, that means you have 95% confidence in your result. If you choose alpha is 0.01, you have 99% confidence. And yes, this is all going to tie into the discussion we already had on confidence intervals. But before I go on and do anything else, I want you to think about what alpha equals 0.05 really means. 0.05 is 5%. The threshold for medical research is that there is a 5% chance that we were duped. There's a 5% chance that if we tried something and we saw a result, that was just a random fluke in the data. This is the reason that follow-up studies are so important. And it's unfortunately something that journalism has been very bad at and has been getting worse at over the course of my lifetime at the very least. Medical research is supposed to be, we did a trial, things look promising, we should follow it up with more trials. But somehow that has turned in our culture into this medical research showed statistical significance. It is the next new thing and we should all rush to adopt it. Sometimes that works out fine, but about 1 in 20 times that someone has that headline in an article in a newspaper, the immediate follow-up is, oh, it looks like we were wrong. After 2 years of trying to use this thing, it's not actually coming up and doing anything valuable at all. Let's throw that all out. Everyone gets disappointed and we'll go back to the drawing board. Right? 5%, 1 in 20, that's what's supposed to happen. That's why follow-up research is so important. We saw a study and showed that the outcome looks promising. The next step is to do a bigger study with more funding, with more participants, with a larger sample size, and let's see if this actually pans out. There's a 1 in 20 chance that we were duped the first time. There's a 1 in 20 chance we would be duped the second time, but put those things together, that's a 1 in 400 chance that we can get through 2 trials. If we do a third trial, there is a 1 in 8,000 chance that we can still be duped. Right. Some unscrupulous researchers know this and have been trying to use it to their advantage. It's an important idea and why statistical literacy is so important. Even if you never perform a statistical test, what does that significance level actually mean? What does it mean to be statistically significant? Statistically significant, I haven't even gotten to yet, but the level of significance here. Statistically significant means that the level of significance has been met. We have a 95% confidence that this is something worth looking into. When you're reading popular articles proclaiming big advancements in medicine or in other parts of science, look at that significance. Is this the first time that somebody has done this, or is this a follow-up trial? How much detail has gone in? How much research has gone in? As a member of the population, as a voting member of the public in the United States, remember that follow-up trials are an important part of scientific research. We conducted one trial, the results look promising. We want to conduct another trial to verify that outcome or to contradict it and tell us to go back to the drawing board. Part of the reason that the journalist community has been so drawn by that first result is that funding for follow-up research has been incredibly difficult to come by. And a lot of funding is provided by government, the National Science Foundation, the National Foundation for Health and Medicine, so on and so on. So be aware that follow-up research is something that's important. To take this from a 1 in 20 chance down to something that's a lot more confident. But again, for our purposes this semester, I can take a step back off of my soapbox. All we're looking at is the one case. Designing the follow-up trial is back up here to formulating your question. And that's something for whichever discipline the question is coming out of. Statistics is just telling you what to do with it once you've got it. Step 5 is another step that we don't really have anything in statistics to say about it. You need to find a way to choose a representative sample and sample them. And how that works is going to vary strongly depending on what kind of research you are trying to do. Step 6 is the step that we're going to focus on in this course this semester. Perform the hypothesis test. I know the whole thing is called performing a hypothesis test, and almost all of it is how do you set up and get the information you need in order to perform that test. All right, performing a hypothesis test is going to involve performing a couple of calculations, looking something up on a table like the standard normal table or another one. And then we will use this information to either accept the null hypothesis or reject the null hypothesis, depending on which is appropriate for the result that we come up with. Let's look at a particular example. The Medical Rehabilitation Education Foundation reports that the average cost of rehabilitation for stroke victims is $24,672, with a standard deviation of $3,251. To see if the average is different at a particular hospital, researchers select a random sample of 35 stroke victims from that hospital and find that the average cost of their rehabilitation is $26,343. And then finally, our question. If we set alpha equals 0.01, can we conclude that the average cost at this hospital is different from the reported overall average? Great. So this scenario has already done the first 5 steps of the process for us. We have a question. Is the average cost for stroke rehabilitation at this particular hospital different from the average cost of stroke rehabilitation as reported by the Medical Rehabilitation Education Foundation? We've already established a variable. We calculated the cost. It's a very obvious variable in this case. We need to set up a null hypothesis and an alternative hypothesis still, but we do already have the level of significance set. Alpha equals 0.01, which is more strict than what I said was the usual, but more strict is better most of the time. So the step that I skipped is the null hypothesis and the alternative hypothesis. That's the first thing that the paragraph of text did not tell us. And we'll follow the basic formulation. The null hypothesis, we're talking about the mean of our population, and we conclude, or we want to be able to conclude, that this is the same as that average that was reported, 24,672. The alternative hypothesis then is that the average cost here is not 24,672. Step 5 of the process is to design the experiment and collect the data. We've already have the data reported to us. We don't have to design anything. That's one of the conveniences of solving problems in class, is that the tedious part of the process is done for us. So we are on to step 6, actually performing the hypothesis test. And the test we're going to use is quite a mouthful. We're going to look at a two-tailed, one-parameter z-test on the mean. Although if I was reporting this as part of a research article, I would just call it a z-test. I wouldn't specify all of that. I'd say it's a z-test, and I would say that alpha is 0.01. I talked about one-tailed or two-tailed prior to collecting the information, and we already have the information, so that skews our perception a bit. But prior to collecting the information, all we cared about is this different. It could have turned out that the cost at our particular hospital was higher. It could have turned out that the cost at our particular hospital was lower. We had no way coming into the situation of making that distinction. And because we had no way of making that distinction, we had no choice but to use the two-tailed test. Our test is a one-parameter test. We are measuring a sample at one particular hospital and comparing it to a known population. Later on, we'll look at analyzing a sample from one group, analyzing a sample from a different group, and comparing them to each other, which is a more challenging test. It involves more calculation and more critical thought. So let's focus on this one for now while we learn what the whole process of hypothesis testing is. It's a z-test. I haven't talked about what a z-test is yet, but I think you can predict based on the name that it's going to involve the z-score. And it's a test on the mean, right? The things we've talked about are averages. That, again, hopefully makes a lot of sense. All right, so to perform a z-test, we're going to need a couple of things. We need to find the average of the sample. And that was done to us. That was how the information on the sample was reported, saving us a step. If it hadn't been, we'd have to go through and calculate an average. You know how to calculate an average. I don't feel like it's worth taking time in this video to go through and do that all over again. Then I talked about the relationship between the level of significance alpha and our confidence level. In this particular case, we had alpha equals 0.01. alpha equals 0.01 is equivalent to a 99% confidence level, right? 1 minus 0.01 is 0.99. Convert that to a percentage, it's 99%. That brings us to our question. Is K, which in this case is 24,672, inside of this confidence interval? If it is, then we will accept the null hypothesis. If it is not, we will reject the null hypothesis and accept the alternative hypothesis. Right. Confidence intervals tell us that with 99% certainty, the true value of the mean is within the interval. And so if the question value, the value that we are asking by our null hypothesis, if that value is within the interval, then the possibility is high that the value for the population is equal to that. If that number is not inside of our confidence interval, then with 99% confidence, we can say that the mean of this new population is not the same. All right. So looking back at our data, I've scrolled it well off of the screen at this point, but hopefully you have it written down in front of you. The average value for our particular cost at this particular hospital was 26,343. And we're looking for that 99% confidence level. Right. So looking up in the Z table, if we want a 99% confidence level, thinking about how confidence intervals work, that means we're looking for values here so that 99% of scores are in the middle, and the last 1% is evenly distributed. So that's 0.5% over here, 0.5% over here. All right. So 0.5% is 0.005. Looking up on the standard normal table, the z-score that corresponds to 0.005, you get negative 2.58. And then all told, to get to the higher one, we have 99% plus half a percent. So that's 0.995. And if you look that up on the z-score table, you get positive 2.58. I mentioned it when we were talking about confidence intervals, but I think it's worth repeating. You should always have the same value, positive or negative, when you look these up, but it's worth looking up both as a quick way of double checking yourself. If you get a different z-score, a different value, in addition to positive versus negative, then things are going to go very badly. It's a sign that something went wrong in your earlier calculation. Go back, think about the standard normal distribution again, check your z-scores one more time. All right. To continue, Constructing a confidence interval, the formula we used before, we take our mean x bar plus or minus the z-score we just calculated, right? The plus or minus is there for the two options of the z-score. And then we need sigma and we need n. Sigma is the standard deviation of the population. This is the limitation of the z-test. We have to be looking at a situation where the standard deviation of the population happens to be known. Luckily for us, in this particular case, the standard deviation of the population is in fact known. It was 3,251. The number of data points in our sample, in this case, was 35. So now we have numbers we can plug in. We want x bar, 26,343, plus or minus z, 2.58, times sigma, 3,251, divided by n, square root of 35. And for that, we can just grab out a calculator. I'll do this in 2 steps. I find that's a little bit easier. 2.58 times 3,251 divided by the square root of 35. My calculator tells me is 1,400. Since my mean was rounded to the nearest whole dollar, I'll round that to the nearest whole dollar as well. And then I take the plus and the minus branches. 26,343 minus 1,418 is 24,925. And then 26,343 plus 1,418 is 27,761. And I know that the mean of the population is somewhere in that range. Now we go back to our null hypothesis and our alternative hypothesis. For convenience, I'm going to scroll up here to where I have them written down. I'm going to copy them and I'm going to bring them back and set them next to everything else we've just been looking at. You don't have to rewrite them, but I want to have everything on the screen at once. All right, there's our null hypothesis. There's our alternative hypothesis. And then in the box, we have our particulars from the z-test. We claim that with 99% confidence, mu is somewhere between 24,925 and 27,761. 24,672 is not in this interval. And because it is not in this interval, we can reject the null hypothesis. If it was in that interval, we would accept the null hypothesis. Right, the null hypothesis said that there was no difference. The alternative hypothesis, what we take if we don't take the null hypothesis, says that there is a measurable difference between the cost at this hospital and the known average cost. I like calling it a measurable difference. We can measure a difference. But I do have to at least mention that very often you will see this written as there is a statistically significant difference. And the language there is problematic for a reason that language is often problematic in mathematics, in the sciences, and less so, but also elsewhere in the academic pursuits. The word significance has changed meaning over the past century or two. When the idea of statistical significance was first being developed, the word significant means that this is a sign. So there is a statistically significant difference, literally means the statistics tell us that there is a sign of difference. There is some indication that there is a difference. That's what statistical significance tells us. In today's language, the word significance means somehow important or large, which is absolutely not what we are trying to convey in statistics. The difference could be minuscule. In this case, the difference was fairly sizable. Right? The difference between 24,000 and 26,000 is about a 10% difference. That's a fairly large jump. You can have a statistically significant difference between a measurement of, say, 10.35 centimeters and 10.36 centimeters. It's a difference of a tenth of a millimeter. That's a tiny difference when you're looking at a scale of 10 centimeters, right? 10 centimeters is about that big, the width of my face. A tenth of a millimeter is about the width of my fingernail. But if we can show that there is a consistent difference, even if it is minuscule, it still counts as statistically significant, right? There's been a push, a couple of different sources have used a couple of different words. I like measurable. We can measure the difference. Again, doesn't have to be a large difference, doesn't have to be a small difference. It doesn't have to be an important difference. It could be a completely useless piece of information that doesn't help anyone at all, right? The difference between your hair growing 10.35 centimeters and 10.36 centimeters over the course of a year, no one's going to notice. But if it is able to be shown, then it is a difference. And that's all that matters. That's all we care about in statistics. Is there a difference? Is the difference large? Is the difference worth the cost? Is the difference a sign of something important? That's for the individual disciplines. That's for wherever your question came from to answer. That's not something that statistics can tell you. I have one last idea that I wanted to mention quickly in closing before I wrap up this video. In this video, I showed you the confidence interval method for performing a hypothesis test. This is one of 3 approaches that are available. The traditional method involves playing around with the z-score directly. If the z-score for x bar is within your range of z-scores for alpha, then your result is to accept the null hypothesis. If your z-score for x bar is outside of that, then your result is to reject the null hypothesis. The third option for performing a hypothesis test is called the p-value method. And the p-value method is the most common that you'll see used in computer software, because computer software has a much better z-score table than we have. So P is the probability that the mean of the population is equal to K, the probability that your null hypothesis is true. And if you put data into a computer statistics software and tell it to perform a z-test, it will produce for you a p-value that you can report. And if p is less than alpha, you reject the null hypothesis, same as we have been. We're not going to look at the p-value method in this course because we don't have access to computer software that will allow us to do that. We're not going to use the traditional method, although you are welcome to if you would like to. All three are mathematically equivalent. All three of them will always give you the same outcome of either reject the null hypothesis or accept the null hypothesis for a particular situation. So there's no benefit to one over the other, except the question of which one is the easiest to understand and which one is the easiest to perform by hand. With that, I'm going to wrap up this lesson. Thanks as always for joining me, and I'll see you next time.